Hello everyone, we are Team Mandelbrot and this video present our solution FinGuard, a real-time Mule account detection system for UPI payments, developed as part of the Cybersecurity Innovation Challenge 1.0. Our work focuses on the problem of Mule account and collusive fraud in UPI, which become increasingly critical as Indian digital payment ecosystem continues to scale. So, moving to the introductions, UPI processed over 130 billion transactions in 2024. While this scale is a success story, it also creates a major challenges for fraud detection. One of the most difficult fraud type to detect is mule account operations, where stolen money is routed through the multiple intermediate accounts uh, within a short period of time. When we look at the each transaction individually, the transfers often appear legitimate. As a result, traditional rule-based system fail to detect the coordinate network behaviors behind the fraud. By the time suspicious activity is noticed, the money has already moved through the multiple accounts, causing a financial loss. And freezing those innocent user account is not a great solution. So the limitations of our existing system, the most existing fraud detection systems rely on the static rule or isolated machine learning models. Rule-based systems are easy to understand but inflexible, easily bypassed. Machine learning models can detect patterns, but they often lack of explainability and still struggle with the network level frauds. Most importantly, current system analyze their individual transaction or historical behaviors but not the relationship between the accounts. The gap motivates us to design a system that looks at fraud from multiple perspective at a single time. So our core idea is simple, just multiple just we just focusing on three things. Okay. F- so mule fraud cannot be detected using a single signal. So we proposed a hybrid detection system that combines three complementary signals. First one is temporal behavior tracking, how an account behaves over the time. Second one is transactional graph analysis, how money flows from across the accounts. And third one is device fingerprinting, how actually collecting the accounts. By combining the three signals, we detect not just the suspicious transaction but organize the fraud networks while keeping the false positive very low. Okay, now moving to the system architecture. This is the core part. So UPI transactions. So UPI transactions first enter our system through a real-time injection layer. So UPI system injection layer, which allow us to handle high volume data. So for handling the high volume data, we are using the Kappa models. Each transaction is then reached through the feature engineering pipeline. So first we have behavioral features. Behavioral features capture the transaction frequency, inflow, outflow, and patterns, and the sudden deviations. Next we have graph features models. So the graph features transaction models as network where accounts and nodes and the transfers are edges. And the third one is device enrichment adds device levels signals that help link multiple accounts control from the same devices. And this feature processed by the multi model scoring engine. So first we have a temporal model based. on markup chains, capture the abnormal behaviors. Next, we have a graph model. So the graph model, the graph neural network analyze the tangential graph to detect the star chain or circular patterns of frauds, and the device correlation module propagates risks across accounts sharing the same device fingerprinting. Now we have the risks aggregation and detection part. The output of these models aggregated using weighted ensemble or generated a final risk score. So we are just taking the weighted value of those three things, and we just calculating the risk factor. So the high risk causes the surface of immediate for investigations, and while the low risk transaction continue without any interruptions. So now moving to the storage part and the dashboard. For handle the low latency UPI payments, we required very quick kind of databases. For so Redis is used for the caching the hot data to meet the UPI latency requirement. For storing the graph kind of data, we just using Neo4 graph database. And for the audit logs, so maintaining the logs and other stuff, so we just using Postgres SQL. And the investigator access flows was just a moment. Oh yeah, it's an investigator. Yeah. So the investigator access flaws caused through a dashboard that visualize that causes and explain why the alerts were raised. So now moving to the decision and methodology. Yeah. So our decision methodology focuses on three fraud patterns commonly seen in the Mule operations. First one is the star patterns. So star pattern is aggregation of the frauds. Next one we have the chain patterns. Chain patterns is a sequential laundering, and third one we have a circular pattern. It's a looping of frauds. So the three patterns are difficult to detect using a traditional system, but become visible through the graph analysis. Now we have the device fingerprinting. Using the device fingerprinting, we can just check the same device is a part of the network or not. We just checking by using the device fingerprinting. Real time real time scoring is achieved using the cache risk signal, ensuring that the fault and fraud detection does not delay the payments. And expected outcomes, our system is designed to improve early detection of mule accounts while maintaining the high precision. It reduce the false positive, improve the investigator efficiency, and operates within the static latency. So most importantly, it is explainable, scalable, suitable for the real world deployment for the India's payment ecosystems. Okay, so as in a conclusion, so FinGuard demonstrated how combining temporal behavior, transactional graphs, and the device intelligence can significantly improve the mule account detections. Thank you for your time and consideration.